Yeah, but I try my best to help you understand here so that when you go back, you don't have to scratch your head over it. So as I said that over beta oxidation, you really don't need to memorize structure, okay? So already take a lot of stress off you. No need to memorize structure. Why do I say that? Right? So if you look at this reaction, so remember this R group is not so simple as an R. You have to remind yourself this R group is really a lot of carbons in there. Right? It's not acetyl-CoA whereby it's only CH3. When it comes to fatty acid, this R is like C16 and above usually. And most of our diet is palmitic acid, stearic acid, oleic acids, right? Depends on what you eat. Olive oil, then linoleic acid, right? So look at this structure. This is a typical fatty acid. This is a straight chain, saturated. Saturated, right? No carbon bonds. And R is C16. Right? So, not R is C16. The total number of carbon is C16. That's why it's palmitate, right? And the acyl-CoA, so it's a palmitoyl-CoA. Why do we call it CoA? Because over here, SCOA, this is the CoA thiol group, right? Linked to the carbonyl or the carboxylic acid group, CO group. Right? If you just look at this, this is a CH. This is actually acetyl-CoA. Right? So starting from the carbonyl group, right? Number 1, okay, we call this carbon alpha. And over here, beta. Okay? So the beta oxidation process is called beta oxidation because we are essentially oxidizing this beta carbon. Alright? Therefore the name beta oxidation. Okay? So let's go through this alpha next to the carbonyl, alpha, beta. Right, the same as ATP, alpha, beta, gamma. So alpha, beta. So we're oxidizing this beta, that's why it's called beta oxidation. So the first reaction is to convert, okay, this alpha, beta single bond to a double bond. And the double bond must be in the trans configuration. Right? Trans configuration means the hydrogen must be on opposite sides. Okay, must on opposite sides. We draw it like that in the 2D version. So now this is catalyzed by this enzyme called acyl-CoA dehydrogenase. And again, when you see dehydrogenase, you must remember that NAD or FAD is involved. So in this case, FAD is involved to remove the electrons and becomes reduced FADH2. Okay? So now the product now, see, I can give you like a very complicated fatty acid, but the same thing happens, okay? Over here, at the alpha-beta bond, make it a double bond. Alright, make it a double bond and then it has to be in a trans configuration. So now, so it becomes a trans delta 2. Okay, this delta just tells us the position of the double bond. I'm sure you have seen it in your Mat Chem or chemistry. And 2 means carbon 2. Right, the double bond is at carbon 2. Carbon 1, carbon 2. Okay, so delta 2. If the double bond is here, then it becomes delta 3. 1, 2, 3. Right, so in this case, it's a trans delta 2, 1, 2, enoyl-CoA. Right, this is called enoyl-CoA. Double bond C and CO is an enoyl-CoA. So, and then after that, there will be a hydration of this trans double bond. Hydration just means it becomes OH. Right? Hydration, the double bond becomes a COH. When it becomes a COH, the double bond is being removed. Alright? Okay? It's being removed. So once it is being removed, then NAD comes again. This is called a beta, right? Alpha beta. Beta hydroxy acyl-CoA. Alright? Beta hydroxy acyl-CoA. Right? So then the beta hydroxy acyl-CoA dehydrogenase then comes in to again remove. Now every time a dehydrogenase comes, it's because you have to remove a hydrogen, right? Because the dehydrogenase will pick up the hydrogen over here. So you can then imagine where is the hydrogen that we can remove? Over here. Okay? Over here, when you remove it, right, it becomes a C double O bond. Okay? Compare it to before. See? Compare it to before. So you are actually adding a double O on the beta. That's why oxidation, right? Beta oxidation. Okay? The beta carbon over here gets an oxygen, so it becomes beta oxidation. And final step, now this looks very much like acetyl-CoA already. So then this enzyme called thiolase, okay, or acyl-CoA acetyltransferase, we just call it thiolase, will then come in together with CoA to cleave this molecule and add another CoA over here on the remaining chain. Alright? So do you see that every pass of this reaction, you remove this portion as acetyl-CoA and you reduce the chain by 2 carbon every round. Okay, so from C16, it becomes C14 and 1 molecule of acetyl-CoA is being produced. Okay, so not so difficult, right? Not so difficult. It's just moving around the bonds, right? To add another acetyl-CoA, CoA molecule over here. So then we have, it's not enough, complete, right? We have to complete this whole process. So we indicate it by a spiral. Okay, we always do it like a spiral here. Okay, 1 pass. So just now 1 pass, we have 1 molecule of, one molecule of acetyl-CoA, right? And along with acetyl-CoA, there will be 2 pairs of electrons given out because hydrogen was removed. So the hydrogen, it has, 2 hydrogen removed. So you have 2 pairs of electrons and 4 protons. And then the chain shortened by 2 carbon. Okay? So this just goes that, okay, we have finished 1 pass over here. So another pass, 1, 2, 3, 4, 5, 6. Okay? 7 more passes. Okay? And then you will have a total, 6 more passes, and you have 1, 2, 3, 4, 5, 6, 7, and the previous one that's being produced, you have 8 acetyl-CoA. So the math is quite simple. If I start with a C16 carbon 16 fatty acid, just divided by 2, you will get the number of acetyl-CoA. Right? Minus 1, you will get the number of cycles. Right? Because the first cycle, because the last round, you will get an extra acetyl-CoA as the product. So if I give you C18, stearic acid, 18 divided by 2, you will get 9 acetyl-CoA, and in total, 8 cycles. 9 minus 1, 8 cycles to give you the acetyl-CoA. Right? So C20, you will get 20 divided by 2, 10 acetyl-CoA, and 9 cycles. That's how we calculate the number of acetyl-CoA. Okay? Alright? So it's not so difficult. So we just use this spiral to indicate the different passes. So this is beta oxidation. So, but it's not complete. Acetyl-CoA, where does it go after that? Right? Acetyl-CoA will then enter citric acid cycle. Right? This is the acetyl-CoA the same way, derived from glucose. This is the central connecting molecule. So it goes to, so we also use this squiggly line to indicate the cleavage of the bond. Okay? So 8 acetyl-CoA will then enter citric acid cycle, complete the process, to electron transfer, and then give us our ATP. Right? We have seen this just now, this part. Alright? Okay, so all these happen in mitochondria. Don't worry about these equations, right? I just want to illustrate to you what it means going through the different cycles. Okay, so don't freak out. I'm not going to ask you to write this equation for me or whatever. Okay, so but you have to understand the concept, how we derive from, this is sterile, right? Sterile CoA, which is 16, 17, 18 carbon. Okay, as I mentioned, 18 carbon. Alright, and then it should be, is it 8 cycles or 7 cycles? 8 cycles. 18 carbon divided by 2 will give you 9 acetyl-CoA. 9 minus 1, this is resulted from 8 cycles of beta oxidation. And 8 cycles of oxidation will give you 8 NADH and 8 FADH2. right? Because just now the previous process we have one FAD H2 produced, one NADH produced, right? Okay, so 8 cycles will give you 8 of each. Yeah? Why do we need that information? Because this will help us calculate how much ATP is being produced, right, by this oxidation. Right? Off the cuff, you can already tell. How do we calculate? 8 times. How many ATP is being derived from this process? 8 times 2.5 plus 8 times 1.5. That will be total number of ATP. Okay, so this line just tells you how you can easily count. Okay, right? This is the first CoA / / This is where the bonds will be broken. That's why you have 9 acetyl CoA. The first one here, second, etc. Carbon units. Right? Okay, and 8 cycles of oxidation. So now let's do some math. Okay. Just now we did math for glycolysis. Total is 30 or 32 ATP, depending on which shuttle system. Now, for this stearic acid, let's get an example. Stearic acid C18. Simplest way is to put down number of the NADH molecules, number of FADH2 molecules, and then calculate the molecules, ATP from here. So from stearic acid to become sterile CoA, the activation step, we have used up 2 ATP over here, right? This is for, remember ATP is being used to carry the stearic acid, right? As an adenylate transition molecule, intermediate. And over here, once it becomes an acyl CoA, it then goes through beta oxidation, 8 cycles, as we have seen. So 8 cycles will give you 8 NADH, 8 FADH. Okay? So over here, and then these, the acetyl CoA will go through citric acid cycle to give you 27 over here, right? Because each cycle of citric acid will give you 3 NADH. So 3 times 9 will give you 27. All right, and we have 1 FAD from the cycle, so 1 times 9 will give you plus 9. Plus substrate level phosphorylation, which is 1 molecule per cycle, so 9 will be 1 times 9. All right, and all these then tells you, okay, what do we do during the electron transport chain? All right, during the electron transport chain. We multiply, okay? Over here, okay, so over here they just added the substrate level ATP molecules here, so 9. So now over here, all these, okay, so 8 molecules, right? So goes through electron transport chain, 8 times 2.5 will give you 20 ATP molecules, right? And then 27 again times 2.5 will give you 67.5. Okay, so this is derived from here. Just move it down, all right, to regenerate it. See, the regeneration of NADH. That's why net is 0, because it's regenerated. Same thing for FAD. You regenerate FAD, right? Minus 8, minus 9. So 8 times 1.5 will give you 12. 9 times 1.5 will give you 13.5. Add all up together, it will give you 120 ATP molecules for stearic acid. Okay? Alright? Did you get this table? Okay? Right? So you get this part, right? 9 acetyl, so you get this. Just calculate the number of acetyl. Okay, so 8 acetyl CoA will give you 8 NAD and then 8 FAD. Right, just remember for NADH, multiply it by 2.5, you get number of ATP molecules. So let us compare it. Okay, if I say that stearic acid is 18 carbon, 3 molecules of glucose will also give you 18 carbon. Right? Just now we saw that 1 molecule of glucose will give you 30 ATP or 32 ATP. So let's multiply, let's take 32, okay? 32 times 3 will give you 96 ATP. Okay, so it proves our point that for stearic acid, the fatty acids really give you higher ATP yield per carbon atom. Right? Okay, it does give you more energy. Right? This is in terms of ATP yield. Just now in the first chart, it was in terms of delta H, which is heat. Kilojoules, heat, double. Okay, again, don't fret about this equation, which I think is wrong. So we calculated 120, but it's 122 over here. So there's some problem with this equation. But anyway, the point that I'm trying to make is not about all these, but the water here. Okay? So you see this grizzly bear, okay, hibernating. How many months does he sleep? Do you know? 7 months he sleeps. Without urinating, without defecating, without eating, without doing all these things, okay? 7 months he sleeps. You wish you can do that. Already some of you doing that in the lecture theatre. 2 hours, not 7 months. So, what happens, right? What happens that help him stay alive? Okay, answer is today's lecture, beta oxidation. Alright, so the beta oxidation will give him all the energy, okay, all the ATP to stay alive and to power his cells. Yeah? At the same time, beta oxidation will also give him water. He didn't drink throughout the whole 7 months, but beta oxidation gives him this metabolic water to replace the water that he breathed out. Right? So when he was sleeping, he breathed out, right? The water will be lost from his breathing. And this metabolic water helps him replace the water. So nice life, 7 months. But in order to prepare himself for this 7 months, you know how much he has to eat. For the 7 months, for the 5 months that he is awake, he has to eat 20 hours a day. Okay? 20 hours a day. It's almost like infusion. And he needs 84,000 calories. Okay? He takes about, when he's sleeping, he uses up about 6,000 calories. You use about 3,000, 2,000 to 3,000, yeah, a day. So you use 3 times, during his hibernation. But he needs to eat 20 hours a day while he's alive, not alive, while he's awake. Yeah, while he's awake, to consume 84,000 calories every day. Okay, so that's why it's basically bad. Right? Yeah? So beta oxidation is important for hibernating animals. For camels, it's also important. Camels, they don't hibernate, but what happens in camel in the desert, right? Very dry, right? Very little water, but he stores lipids in the hump, okay? He stores his lipids in the hump, and this beta oxidation will give him the water he needs, all right, for long periods of dryness. Okay, all right. So this importance of beta oxidation cannot be neglected. It is not only when you are fat then you have beta oxidation. It's for a normal human being. Right, so far we have only talked about even number, right? We talk about palmitic is C16, stearic is C18. You divide all these numbers, you get nicely divided by 2. 16 divided by 2, 18 divided by 2, 20 divided by 2. So what if you have a 19 carbon fatty acid, what happens? Which is quite rare in our diet. You don't really get an odd number fatty acid in our diet. You usually get an even number one. Okay? Right? Thank goodness for that. Because this one, odd numbered fatty acids, usually occurs in plants and marine life. Okay? Only in plants and marine life. And so when they go through the normal beta oxidation, right? But the only problem is the last step. So the last step, instead of making acetyl-CoA, it has what we call propionyl-CoA, right? So you have one more carbon left. See, acetyl-CoA is CH3, right? But over here you have one more carbon. 1, 2, 3, 3 carbon. Therefore, propionyl S-CoA. Okay? So this propionyl-CoA in plants, usually in plants and in marine, and sometimes in our diet, Okay, in our diet we ingest these, okay, not as part of our diet, but as additive, food additive. Certain food additive contains all these odd number fatty acids. So we also need to break it down, but in a very small proportion. So the propanol-CoA will then be carboxylated, all right, carboxylated by propanol-CoA carboxylates, okay, in our body. So you have carbon dioxide over here coming in, right? It will be carboxylated, right? And then rearranged, the COO group will move up on top to give us our succinyl-CoA. Right? We said that this succinyl acid is a symmetrical molecule. Succinic acid is COO, CH2, CH2, COO. Okay? But with a CoA, okay, at the end, that is a succinyl-CoA. Sounds familiar. Right? Succinyl-CoA will then enter the citric acid cycle and participate in the substrate level phosphorylation. Because this is a high energy compound. Anything CoA is high energy, okay? Anything CoA is high energy, like acetyl-CoA, succinyl-CoA, and all your acyls-CoA. They are high energy compounds. Okay? So now it goes into the citric acid cycle. Fortunately for us, this doesn't accumulate. We can use it for our energy needs. Okay. Now, again, another problem. We have also just talked about saturated fatty acids, no double bonds. What if we have monounsaturated fatty acids, right? Which is common in our diet, right? So instead, we have, let's say this example of oleic acid, okay? So oleic acid has oleoL-CoA, and it has a double bond over here, okay? So if you do it by the normal way of beta oxidation, you can cleave 2 carbons at one go. So remove 2 carbons, remove 2 carbons, remove 2 carbons, okay? Three cycles, you get 3 acetyl-CoA. But once you reach this double bond, you are kind of stuck. Why? Look at the structure. Okay? The arrangement, the double bond becomes a cis configuration problem. Why? Because the enoyl-CoA hydratase, right, the enzyme that adds the OH group to the double bond, cannot catalyze a reaction in the cis configuration. It can only work in the trans configuration. Okay? Right? So we need extra help now. This extra help comes in the form of this enzyme called delta-3, delta-2, enoyl-CoA isomerase. Okay? So just now we said this is carbon, this is carbon 1. 1, 2, 3. 1, 1, 2, 3. Okay, so this is the third carbon over here, right? So the double bond is at the third carbon, delta 3, and it is called cis. Okay, now the name of this isomerase tells you what it will become. It becomes a C2C3. Okay, so over here, what it does basically is to move this double bond to this position. Okay. 1, 2, 3, 4. Okay, now it's 3, 4. Alright? So the isomerase will come in and move the double bond to 2 and 3. See? Alright? And then swap the configuration from from cis to trans. Right? So now it becomes the trans delta 2. Then over here, the enoyl-CoA hydratase can then work and add the OH group over here and subsequently cleave this double bond to give you your acetyl-CoA, and the process then continue. Right? So even with this isomerase reaction or with this double bond, there's no loss of acetyl-CoA. You still get 18 carbon divided by 2, which is 9 acetyl-CoA. So you have 3 here plus 6. So total is unchanged. It's still 9, okay? If compared to a saturated, still the same. You just need to work on this cis double bond. Okay? Alright? Now, complexity. That one was just mono with one double bond. What if we have more than one double bond? What happens? Okay, let's take an example. Okay, now we need another enzyme to help us. So this one you see is 9, 10, 11, 12. Position 9 and position 12. Again, just do the normal process. Cleave it by 2 units, 3-acetyl-CoA. Right, and then you get stuck here. This is the same example from just now. So you have the 3,4, right? So in the monosaturated example, we use the enoyl-CoA isomerase to move this double bond to 2,3, which is the alpha-beta, right? Because the CoA hydratase can only work on alpha-beta transversion. All right, so once this first problem is solved, no problem now. First problem is solved, continue again. Then you can produce acetyl-CoA. But when this acetyl-CoA is removed, you've got another problem. Okay? Over here, it is not in the right configuration again. Okay? So then we have another enzyme to help us out a little bit. Over here, this is the di-enoyl-CoA reductase. Di-enoyl. So we have 2 enoyl here. Okay, right? So the di-enoyl-CoA reductase will then take away one hydrogen. Take up one more hydrogen. Okay, take up one more hydrogen to convert this bond. Okay, to remove the double bond over here and move this double bond to 3,4 position. Right. Once it moves to 3,4 position, the problem is still not solved. It needs to be in 2,3. Okay, it needs to be in 2,3 position. So the isomerase comes in again to move this double bond over here. Okay, so you see the situation is the same now. Okay. Okay. So the polyunsaturated fatty acid will require 2 enzymes. Okay, 2 enzymes to work compared to the enoyl-CoA isomerase. Alright, I'll stop here for today. The ketogenesis will continue for the next lecture. Go back and digest it a little bit. I haven't had many questions from the lectures. So please spend time revising. Yeah?